All right, how you doing, Mr. Dean here? We are at the beginning of modeling and optimization in calculus, and we're talking maximizing area of inscribed rectangles. Why do we do this? Historically, optimization problems were among the earliest applications of what we now call differential calculus. There are many, many real-life applications of this. Let's get started here. There's a great website, demonstrations.wolfram.com. You can check it out. The application or the website itself wasn't fast enough to run for this, so I took some screenshots, but you feel free to go onto that website and check it out yourself. It's interactive. And what it is they have a number of different curves you can try out. This black curve is 4 plus x over x squared plus 1. And we're trying to find the largest rectangle that we can fit underneath that curve, the largest area of a rectangle. So there's a little slider you can see here, up here, there's a slider that you can use in the actual website. And I chose to be about, x to be about 1.1, and the area was pretty big, it was 1.4. I thought that was pretty large. And I moved the slider over a little bit so that it was just small, but a really tall triangle. And I got that the area was 1.25 or so, a little bit smaller overall. But I realized from this graph on the side here, the area of the rectangle, that that area that I had was represented there, or represented by that little green dot there, if you can see that. But really there was a larger area up there. So I hadn't hit the maximum yet. And we're going to talk about how to find a maximum area under a curve. We'll choose a little simpler graph to try, so we can do it on our own without necessarily needing a calculator or a Desmos or anything. There are 6 steps to finding the answer here, and the last 2 steps sometimes we don't even need it because it doesn't ask for that information. But we graph the curve, we inscribe the rectangle. Inscribe means touching along the edges underneath it, and along the x-axis, so it doesn't go below the x-axis. We find a formula or a function for the area of the rectangle, and then we find the derivative of that. We find the derivative of the area, and we set it equal to 0. And where that x is located will be the maximum area. And then optionally, we write the 4 coordinates of the corners of the rectangle, and we find the actual largest area possible. So let's get going. So there's the 6 steps already done. Here's the problem, negative x squared plus 8. I've already started it off. I have kind of want to set that a little bit better. The parabola is facing downward because it's negative x squared, going through at 8. And really the coordinates where it crosses the x-axis aren't really necessary here, but we're going to be crossing at the square root of 8 and at the negative square root of 8, which is a little less than 3, at 2 point something, like 8 or so, I'm not sure. And we have our green rectangle underneath. All right, now the area of the rectangle, well, the bottom of that rectangle is going to have to be 2x because it's reaching out in one direction out to an unknown x location, x coordinate. So on the other side we have also the same distance, x in this direction, so altogether 2x. And our height is y. Now our height is y, and y is given as negative x squared plus 8. All right, what we're going to do then is that's our formula for the area. We're going to multiply those two, width times height. We're going to find the derivative of that, set it equal to 0, and that'll give us an answer for x. And that x will be the perfect x that makes that green rectangle the largest. So I'm going to show you the ending, by the way. I'll show you the ending. The area you can see down the bottom, 17.39. That magical x number is 1.63. The y is 10.67. How does that all happen? I'm going to show you all the calculations, but I just wanted to go over the overview of it all first so you didn't get wrapped up and bogged down in the calculations. But the calculations look like this. You get the width times the height, so 2x times the negative x squared plus 8. I went down, I found I did find that set it equal to 0, I found the derivative. It turned out to be 3x squared equals 8, and go on, and we have x is plus or minus square root of 8/3, which is plus or minus 1.63 as a decimal. Now we're going to throw out the negative 1.63 because negatives don't make any sense in this problem. We're talking about distances. All right. So x is 1.63. I plugged x back in again to our original function to find out what y was. It's 10.67. And then I plugged it into our area formula. Either one, I guess both of these are area formulas. and I got 17.39. That is the largest area of a rectangle that's possible underneath that curve. Now sometimes they give you parameters, like same problem, but now we want to look just between 0 and 5. All right? Well, we had said that it crosses right around square root of 8, all right, which is about 3. 5 is to the right of that. So we're only going to be looking between 0 and 5, all right? So we have a slightly different problem in here, and that is that our area, we bring that up, our area now is just x times negative x squared plus 8. And we multiply that out, and we get negative x cubed plus 8x. I found the derivative. We have negative 3x squared plus 8. Similar to last problem, except last problem we were able to go into the negatives over here, and now we're not. We can't get as far as 5, because that's outside of our curve. So anyways, we take the derivative, and we get a very similar square root of 8/3 answer for x. And you can go back in and find out what the y is, just like we did before in the area. But those are the steps. We graphed it. We set an equation for the area. We found the derivative of the area. Set that derivative equal to 0, and that was our magic answer for x. All right, let's take yet another look at a different problem, but it's in a similar vein. Now we're moving it over so that the domain that we can look at is between -1 and 5. The only thing that changes, of course, is that domain. So our width now is x plus 1, all right? Because it's x to get back to 0, but we go all the way to -1, all right? And that's adding 1 on to the width. So we have a slightly different look in our area formula. So I kind of skip that step. We'll go back. The area now is then x plus 1 times, once again, that same y, negative x squared plus 8. And then I multiplied it through, and I found the derivative. And we set it equal to 0. I found the derivative there, didn't mark that. And it turned out that one was factorable. We're not going to get very nice, easily factorable answers very often. So if you can't factor it, you could use the quadratic formula. Or we could even, if allowable, if we allowed to use a calculator, we could find the graph of that function, and then we could find out where it goes through the zeros, or where it goes to the x-axis at the zeros by using the calculator. You get the same answer either way. This one was factorable, and I got x equals 1 1/3. I plugged 1 1/3 back into my original equation to get what y was, and then I multiplied x plus 1 times y to get the area, remember, because that was my original formula, x plus 1, and that's how I got the 14.52 that you see at the bottom. All right, different problem, because all those examples were kind of based on that same curve, negative x squared plus 8. So we're going to go to now a straight line, negative 2x plus 12, and we're restricted to between 0 and 10. So go back to your steps, draw the graph, draw the curve. In this case, it's a straight line. Draw a rectangle underneath it. So there we go. I don't know what this is at all, what the rectangle is going to look like, if it's going to be that wide. That's my best guess. I do know that the x-intercept is going to be 6. And so this 10 here is to the right. It's to the outside. It's not inside that curve. That's okay. We can go all the way, though, to the left-hand side to 0. And all these graphs are above the x-axis, remember, so we're not going to go below the x-axis at all. All right, so we just come up with a formula for our area, which is, of course, the bottom is pretty easy. We don't know what it is, but it's x, and the height is negative 2x plus 12. I multiplied those through, and then I took the derivative, and it looks like negative 4x plus 12. My next step, hopefully you can guess it, is to make that equal to 0, because the derivative is I can solve for 0 there. It's going to go through the x-axis, and that's going to have its own 0. So I'm going to, let's see, maybe factor out a negative 4. I think I did that right. All right. It only has one 0, and that is x equals 3. There is no 0 at 0. Oftentimes we see when we factor out a number and a letter out here like negative 4x, there will be a 0 at x. But this is just negative 4. It's not negative 4x. This outside part, I could have divided by negative 4 on both sides, and it would have gone away. So we have an x of 3, and that means that our rectangle is a 3 by 6 rectangle because I plugged in 3 into this. I got into my original function, and I got negative 6 plus 12. So 18 is my largest area there. How about that? Now let's do a more complicated one. So here we go. We've got 4 plus x over x squared plus 1. That was the function that was on that original slide I showed you where the Wolfram alpha was located. And I had no idea what this looked like as a graph. I didn't know off the top of my head. So I did go on to Desmos. And it is the darker red graph is this one. So the red graph. And the blue graph, the reason that's there, is because I didn't want to go through and find the derivative when it's equal to 0. I did actually go through and find the derivative, but where it's equal to 0 was too much of a hassle. It's beyond what we need to be worried about. So I took the graph of the derivative, and I didn't write the derivative here, but the blue line is a graph of the derivative. So what are we interested in about the derivative again? We're interested when the derivative of the area is 0. And it's right there. It's pretty nice in Desmos. You can just literally press, if you're on your phone, you can just literally touch the screen. If you're in Desmos, bring your mouse to there, and it'll tell you that you are at 1.281. If you're on your TI-84 calculator, you have to do a whole lot of left-bound and right-bound calculations, but you'll still get the same answer. So I found that the derivative, the highest, the x that makes the volume greatest is 1.281. So that's where I am. I found it. X is 1.281. Then I took that 1.281 and I went back into the original formula in red and plugged it in, and I got a number that was really close to 2. And you can kind of see if that's my rectangle, I think it really should be closer to 2. There was almost no gap. It was like 1.99. And anyways, I found the area by multiplying the x times y. And I got 2.56 as the largest rectangle that can fit in there. All right. You can just imagine there's lots of others that have a possibility that can fit in there, but that is the largest one. All right. Hey, that's all we got. We'll see you in class.